When we're evaluating limits, there's an interesting class of problems that are based on piecewise functions. These functions that are defined differently, have different formulas on different intervals. And these kinds of functions, we can tell pretty quickly where the function is clearly continuous. For example, when x is less than 1, we have the simple formula minus x plus 1 is a straight line. That's going to be continuous everywhere. And if x is larger than 1, then we're going to use a parabola x squared minus 1, and that's continuous everywhere too. So the only problem point, of course, is going to be the transition between those two definitions. The transition between the two intervals. Because we don't know what happens as we stitch those two things together. So let's focus in on that and see what kind of behavior comes out. There's a little complication with this new scenario though. When we were looking at graphs before, it was pretty clear that whether we came from one side or the other, we always ended up at the same point. However, it's just as possible, especially with piecewise functions where we have a different definition or a different graph or function here, that we might end up at two different points, depending on whether we're approaching from one side or the other. We're going to formalize that with the idea of a two-sided limit. That's the case here where we have limits coming from both sides at the same time, and decomposing that into asking, well, what happens if I come from the left? And that's what we're going to call the left-hand limit, and where the notation we're going to use is x approaches c with a little minus sign in the exponent. So from negative values is the idea, or from negative infinity. And we're also going to have the right-hand limit. That's when we approach from above, is another way to phrase that. And for that, we're going to use a positive sign in our limit notation. Let's apply that definition to this question here. We'd like to figure out what happens to this function as x approaches 1. Well, to do that, because we have two different behaviors, we're going to need to evaluate both one-sided limits. And that's fairly straightforward. So here we're going to go through, we're going to approach 1, and I'll do this in color to emphasize it. I usually do the left one first. And the point of that, or the advantage of using that one-sided limit, just a quick graph sketch here, for approaching 1 from the left, what we're guaranteed is, if we're approaching from the left, is that x is definitely going to be less than 1. We're approaching from this side, then we're only talking about x values that are less than 1. Oh, well, conveniently enough, we only have one formula that applies for that interval. It's no longer h in the more general case with both formulas and the whole complexity. If we're approaching from the left, then we're always less than 1. And so we're always going to be using this formula. And that lets us simply sub in, because this function is continuous, and we're approaching 1, we just have to sub in 1. We get negative 1 plus 1, which is 0. And that's a nice finite number. So just as a parentheses, that limit exists and is fine. Let's see what happens when we come from the other direction. Well, it's going to be the same idea. Notice we put this little expression of a plus here in the exponent just to indicate the direction. Let's take this one in green. So now we're going to be coming from larger values than 1, or x values that are above 1 notationally. Tying this back to our function h, that means the formula x squared minus 1 is what's going to be in play. So we have x squared minus 1. Now again, the piecewise nature of h over the whole real line doesn't matter. All we're worried about is the stuff on this interval here graphically. And because we only have the one thing to worry about, we can simply sub in the values now, because x squared minus 1 is continuous. And so we'll get 1 squared minus 1, which is also 0. All right, let's go back to our definition for a moment. We found the right-hand limit exists and equals some number. Here it's 0. We found the left-hand limit exists and it also equals 0. If both of these exist and equal the same number, then we can say the overall limit exists as well. And so the two-sided limit as x goes to 1, it's not a big notation difference, but there is a conceptual difference of our function h of x is equal to 0. With the limit determined, now we can talk about the continuity at the point x equals 1. And let's do a sketch to help us there. Let's put the point 1 on here. What we said was if we're approaching 1 from the left in the x direction, then we're going to end up closer and closer to 0. And when we approach from the right, we also end up closer and closer to 0. And we can actually use h of 1. Then we can use this formula because this applies when x is less than or equal to 1. We can apply that, minus x rather, plus 1. We're going to end up with a 0 there. And so the actual filled in circle that we get is at that point as well. What's the rest of the graph look like here, just to reassure ourselves? Well, this is a graph of y equals 1 minus x. That's a graph that has an intercept of 1 and a slope of -1. So this is the graph of a 45-degree line down. And it would keep continuing if it wasn't for the fact that we define this only up to the point 1, then we stop. What about the other one? Well, this is a parabola. Y equals x squared is the standard parabola centered at 0, 0. But then we shifted down by 1. And then we'd have a parabola that looks like this. But it only kicks in once we get past 1. And so we would have that kind of shape. So the entire graph would be this straight line here, followed by the curve. And as we determined with the limit and the value existing here, we would say h of x is continuous at x equals 1, both because of the graph, but because of the other work that we did, we had the three conditions that h of 1 exists. We could get the value at 0. We had that the limit as x approached 1 of our function also exists. And last but not least, the limit as they approach 1 and the actual value at 1 both were equal to 0. They equal the same value. That was the filled in dot in our graph here. So all these conditions were met, so we could say our function was continuous at x equals 1. Graphically, we could draw it with one pen stroke. Having seen the definition and where things work out nicely, it's worth looking at the counterexamples where maybe the one-sided limits exist, but the overall limit does not. In this case here, that would be a function where we have a point where there might be a discontinuity, well, there will be a discontinuity in this case, where we come from the left-hand side and we sneak up on a value, but when we come from the other side, we approach some different value. And notice it doesn't matter, we could fill in one of these circles, it wouldn't change the limit properties because the limit doesn't care what happens at the point. It cares what would we approach and what value would we approach from the left and what value would we get closer and closer to from the right, and ignores the value at, in this case here, what we call the value c. It's also possible to have a number of other cases where one of the one-sided limits might not even exist. For example, we might have the graph from the left approaching some nice point, but then at that same coordinate, the other function, say in a piecewise scenario, might shoot off towards a vertical asymptote. And there, what we would say is the limit as x approaches c, call that c, from the right does not exist. The other limit would be fine, it would equal some number, say 4, but this limit here shoots off towards infinity. It could also happen, for example, with the graph y equals 1 over x, where you actually have two different asymptotes. So the limit from the left doesn't exist, as we approach 0. The limit from the right also doesn't exist as we approach 0, but they approach different values. This approaches negative infinity, and this approaches positive infinity.